Pete and Ty, the math guys.
Pete and Ty, the math guys.
Berg.
Hey, we are Pete and Ty, the math guys.
Starring Bergen.
Yeah, him too.
Enough dilly-dallying, let's get into it. Throughout calculus, limits occur quite often. Limits are defined as the y value when a function is approaching a specific x value, but never quite reaching it. The approach, coming from both sides of the x value, gets infinitely close without reaching the point, similar to the behavior in a asymptote graph. Let's show you an example.
So as you can see with the first example, we can implement direct substitution with limit of f of x as x approaches 1 is equal to x plus 3. So simply to do this, all we have to do is put the 1 from here into the function, and we get the limit of f of x to equal 4. Unfortunately, with the second example, we cannot quite do the exact same thing. As limit of f of x is approaching 4, unfortunately, it will make the denominator undefined. So instead, we have to take the conjugate approach. So simply, all we do is multiply the top and the bottom by the conjugate. And that leaves us with 1 over x minus 1 over 4 over x minus 4 multiplied by 1 over root x plus 1 over 2. From there, all we have to do is find a common denominator for the numerator, leaving us with 4 minus x over 4x on the top. After that, we can move the x minus 4 and the 1 over root x plus 1 over 2 onto the denominator where the 4x is, leaving us with this on the denominator. And we can also factor a negative out of here, leaving us with negative x minus 4. From there, all we got to do is cross out the x minus 4 here, the x minus 4 here, canceling out and making a 1, leaving us with negative 1 over 4x multiplied by 1 over root x plus 1 over 2. From there, we can take the x approaching 4 from the top and put it straight into the function, leaving us with negative 1 over 16.
And that's how to do a limit.
Another important distinction is left versus right-hand limits. These occur when you have a piecewise function and the specific x value, or the specific limit at an x value, is not the same on both sides. In this case, we use the notation of a negative sign and a positive sign to indicate the left and right-hand limits, respectively.
So here we have our piecewise function and our domain, x plus 3 when x is greater than 2, and 2x plus 5 when x is less or equal to 2. So on this side, we have our x plus 3 part of the function, and as it's approaching 2, it comes with a value of 5, and that's approaching from the left-hand side, as seen with the negative symbol here. On this side, we have the 2x plus 5, and as we plug in the 2 for the x value, we get a value of 9 as indicated by the plus sign here. This left-hand limit and right-hand limit are not equal, which means there is no limit exactly at x approaching 2, meaning the graph will never approach there by itself. You can also demonstrate this by using a graphing calculator.
Because if you're like me, I don't want to use all this fancy work. So what you're going to want to do is take your equation, in this case we're going to use x plus 3, hit graph, you got your graph there, second trace, go down to value, and then insert whatever your limit is. So let's say it's going x to 0, enter, and it gives me a y value of 3, so that's your limit.
That's all.
Did you hear about that Burger kid? The only reason he's on here is because he won a contest.
He's so annoying, man. I swear to
Stop.
Hey! Jesus Christ.
Oh, I'm getting out of here.
No, please!
Hey, did you know you could find out when a function is above 0 with a few easy steps? First off, what you need to do is get your graph and get your equation here, and then you got to find your x-intercepts. In this case, we have negative 5 and 2. Get it in a number line format, and then you're going to want to choose numbers between negative infinity and your first x-intercept, and then your first x-intercept, and your second x-intercept, and your second x-intercept, and infinity. In this case, we're using negative 7, 0, and 8. When you plug these numbers in to your original equation, you'll get either positive or negative values. And that's how you know when your graph is above or below 0. And then in this case we have positive from negative infinity to negative 5, negative from negative 5 to 2, and positive from 2 to infinity. And then this is how you write that out. So f of x is greater than 0 at negative infinity to 5 in union with 2 to infinity.
Another important distinction in calculus is continuous versus discontinuous. So as you can see, in these 3 different circumstances, we have 2 that are not continuous and 1 that is. As you can see, if you have a graph and there is a jump and the left-hand limit does not equal the right-hand limit at any value, you have a discontinuous graph. In the same situation, if you have a point of discontinuity at any point in your graph, it is also not continuous. But finally, if you have a straightforward line, a nice parabola, any type of curve that is not interrupted by a jump or a point of discontinuity, you have a continuous graph and you are good to go.
So, my fellow students, did you know that the slope of a tangent is also a limit? That's right. A tangent is a line that branches off of one point of a curve. A tangent can also be in a conversation. Conversations are cool though, like you're talking to a person and they talk back, human connection. It's really interesting and I don't get a lot of it.
So we were saying a tangent line is also a limit because as you approach the point connecting the curve and the tangent, the h value, which we'll cover in 1 minute, gets smaller and smaller. So as you can see here, if you have a secant line with 2 points on the circle, with the line intersecting through the circle, as the distances, the h value, approach 0, and as the dots get closer and closer together, eventually when they finally meet, you have a tangent line.
Now we'll discuss h values in a tangent equation. First principles in finding derivatives. Basically, as 2 points approach a difference of 0 distance units between them on a secant line, tangent line begins to form. Once that distance has reached 0, for this reason, first principles allow us to find the slope of a tangent line, otherwise known as the derivative. So our equation f at x plus h minus f at x over h help us solve fully and primitively how to get the slope of a tangent line. When using the formula, plug in your equation of f at x where you can. So here, but on this specific location here, what you'll do is you'll plug in your f at x, but you'll add an h to it. So it'll be 3x plus h squared. So from here on out, you have your substituted equation here, and you'll solve. You'll expand this squared, so you'll have 3x squared plus 6xh plus 3h squared minus 3x squared. So here you can you can cancel out the 3x squared as one's addition and one's subtraction, crossing them out. From there you'll have 6xh plus 3h squared over h. So you'll have an h in every single factor here. You'll be able to factor it out, canceling out this one as this one here on the denominator. This h value on the denominator, it's important to cancel out because as h constantly approaches 0 in the tangent line, the h on the denominator will always make it a DNE or discontinuous. So from here, we have 6x plus 3 times h, and once we get to our limit, h is 0, plug in 0 for h. Once you get here, f prime of x, or the derivative of f at x, equals 6x.
In this next part, we are going to be looking at how to find your slope of your tangent at a certain point. So you will start with your original equation, which in this case is x to the 4 plus 2x squared. And the first thing you're going to want to notice is that we're looking for the slope of the tangent at x equals 1. And the first thing we're going to have to do is find the y value of x equals 1. So it's pretty simple. All we have to do is plug in the 1 to our original equation, and we'll end up with a y value of 3. So we're going to be looking for the slope of a tangent at the coordinates 1 and 3. Next, we're going to use power law to get the derivative of our original equation, and it will end up being 4x cubed plus 4x equals mt. And then all you have to do is add in your 1 into the derivative that you just got, and you'll end up with 8. From there, you're going to want to plug the 3 values that you've gotten, so the 1 for x, the 3 for y, and the 8 for m, into this equation over here, and then you'll end up with y minus 3 equals 8 bracket x minus 1 bracket.
So those trig derivatives we were talking about earlier on.
Indeed.
Hey!
Tricky. Oh.
You didn't tell me you were filming today.
Oh yeah, we forgot.
How did he know?
I don't know.
No problem, no problem, guys. Looks like I arrived just in time to teach the kids how to do trig derivatives.
Okay, didn't he
My
drop this
favorite.
class?
I'm pretty sure he dropped it.
Okay.
You know what?
What?
We're not gonna need your help for this. I think
You know,
No.
you've got a
No,
lot on your
I'm
plate.
too
I got
smart.
this. I got this.
Okay.
Hey, let's go this way, buddy. Let's go this way. Yeah.
So, let's get to some trig derivatives. As you can see here, we are starting with the equation of cos x plus 2 over cosecant 3x. Now, just the same way that we did with the normal equations, we now have to do the exact same thing to find the equation of the tangent line. So in this case, we're looking for the equation of the tangent line when x is equal to pi over 2. So firstly, we need to find our y value for our x. All we have to do is plug in the original equation with pi over 2 as x. And because we have cos x here, when cos is equal, or when cos is multiplied by x over, or pi over 2, we get 0. So 0 plus 2 on top, and cosecant is really equal to 1 over sine. So 1 over sine 3 pi over 2 is actually equal to negative 1. So in the end, we get 2 over 1 over negative 1, which is 2 over negative 1, which is equal to negative 2. So now that we have our y value, we can go directly into finding the derivative of the original equation. As you can see with this, we need to be using quotient law. And quotient law for trig is a little bit different than the originals. So, first we need to identify what f is, what g is, what f prime is, and what g prime is. And that's what we have on the left side over here. Once we get that, we need to fill it into the quotient law, which is f prime g minus f g prime over g squared. And as you can see, once we do that, we get a very long line of trig functions, which I will not recite to you right now. But as you can see, cosecant 3x crosses out here, it crosses out here, it crosses out here, and the squared at the bottom cancels out as well, leaving us with negative sine x plus 3 cos x cotangent at 3x plus 6 cotangent 3x over cosecant 3x. From there, all we have to do is sub in the pi over 2 that we have from the beginning of the equation, and we get negative sine x, or negative sine pi over 2, which is equal to negative 1. We have 3 cos pi over 2, which is equal to 0, so 0 times anything will always equal 0, so we're left with that. And cotangent 3 pi over 2 will equal 0 as well. So we end up with negative 1 plus 0 over negative 1, because cosecant 3x is also equal to negative 1. In the end, we get negative 1 over negative 1, which means that the slope of our tangent line is equal to 1. Once we do that, we can honestly just put it back into the original equation of y minus y1 is equal to mx minus x1. We get y plus 2 from the negative 2 we have over here. We get the 1 from the slope of our tangent line, and we get the pi over 2 from the x of the original question, leaving us with y plus 2 is equal to 1 times x minus pi over 2.
Hey guys, I snuck away from the other two. It's getting a little bit rowdy and I got a little scared. I hear them around here somewhere, I think. But I'm going to show you some illegal derivative finding methods so you don't have to use first principles every single time. So we're going to start with power law, the most easiest and most common. So we have the formula for it is n times x to the power n minus 1. So for our example here, we have 3x to the 5, the exponent 5 being the initial start for our variable n. So we're going to drop down that 5 and multiply it by the coefficient 3 to get 15x, and that subtraction of 1 is going to give us the 4, giving us an answer of 15x to the 4. Next we have product law up here, and it helps you out when it's a little bit of multiplication that's jabbing you right in the ribs. So the equation for it is f at x equals f prime times g plus g prime times x, f. It's kind of like a mirror image you got there. So our equation is going to be 2x squared times 4x minus 1. And our f value being 2x squared, our f prime being 4x, our g being 4x minus 1, and our g prime being 4. So with the constant here, that minus 1 special thing happens with the power law. Because everything that doesn't have a variable of x with it has a power of 1. So we have negative 1 to the power of 1. Now, and once we subtract that 1 using the power law, gives us a power of 0, and anything to the power of 0 is 1. So it's basically just getting rid of it. And so here we have we're setting up our equation, and our equation becomes 4x times 4x minus 1 plus 4 times 2x squared. So that all simplified down once you finish that is f prime of x equals 24x squared minus 4x. And that's product law for you. So then we have chain law to the right here. And its equation is kind of hard to write out. So the easiest way to remember it is the derivative of the outside times the derivative of the inside. And the way we get these derivatives is, you guessed it, power law once again. So our question today is 4x squared, all of that to the power of 3. So our derivative of the outside, which we're using as the brackets in the 3, would become 3 in brackets, the 4x squared, and then subtracting that 1 at the top to 2. And the inside function, 4x squared, becomes 8x using power, the 2 times the 4 subtracting 1. So then we have underneath here our final and more verified answer as we brought that 8 to the front. It's 24x times 4x squared. So that's how you use chain law, product law, and power. So a combination of power and chain law is seen here. So here on the bottom left-hand side of it, we have a mix of chain power and trig derivatives as well. So we have our initial equation of sine x squared 2x, our angle being 2x. And so we have our outside function of sine x squared. And so the derivative of that would be 2 cos, because that 2 drops down in front, and sine is cos as a derivative. Now the inside function, the derivative of that, would be 2. So the 2 would also bump out front to it as well. Our final answer being 4 cos 2x, our angle being 2x. And so that's how to do power, chain, and trig derivatives. Because the one trick to remembering is, if you have sine x, your derivative of that will be cos x, and then negative sine x, negative cos x, and back to sine x. It's kind of like a cycle. So now we have here one last trig derivative or product equation. So our equation is sine x times cos x. Our equation f prime times g plus g prime times f. Our f being sine x, f prime being cos x, g being cos x, and f prime being sine x. A little bit, my apologies, negative sine x, a little bit backwards there. So our equation cos x times cos x plus negative sine x times sine x. And then once we multiply those through, it'll be cos squared x minus sine squared x. Now I think I hear them coming, so I might have to get out of here quick.
So here we have implicit differentiation, and implicit differentiation is a little bit more tricky than the other few. So let's get right into an example. Implicit differentiation happens when you are trying to differentiate more than one variable. So as you can see with our example, we have x's and y's intermingled in the question. So the first thing you need to do is find out what the x value is. Right now we have y cubed minus xy squared is equal to 4 when y is equal to 2. So simply all we have to do is put the y equals 2 into the original equation like so, and we are able to solve to find x to be equal to 1. From there, we have to do what we always do, and we have to find the derivative of our function. So starting from the left side, we have y cubed. We need to make it 3y squared using the power rule. Of course, whenever we take the derivative of something that has a y in it, we need to make sure that we keep that dy over dx in it as one of the factors. From there, we need to differentiate minus xy squared. So we just need to do a bit of product law like so, and we will find it to be 2xy dy over dx plus y squared. And of course, when we differentiate 4, we just get 0. From there, we can distribute this negative sign into the equation, and we can put this negative y squared that we got from here over to the right side, giving us 3y squared dy over dx minus 2xy dy over dx is equal to y squared. From there, all we have to do is factor out a dy over dx, leaving us with that as a factor with 3y squared minus 2xy is equal to y squared. After that, we can take what we have gotten out and put it under the y to get us y squared over 3y squared minus 2xy. And as each single term in this equation has a y in it, we are able to take off the exponent from here, an exponent from here, and the y from here, giving us y over 3y minus 2x. From there, we know what y is equal to, and we know what x is equal to. So we are able to fill in y as 2, we're able to fill in y as 2 here as well, and we're able to fill in x as 1, giving us 2 over 4, or 1 over 2, meaning that the slope of the tangent line in this equation is equal to 1 over 2. Curve sketching, an essential part of calculus. Basically, what we're doing with curve sketching is we're taking an equation and we're able to graph it without actually using a graphing calculator. To do that, we need to use almost every single skill that we have learned in Math 10, 20, and 30, as well as calculus.
All right, let's get into it. Get the boom out of the shop.
Come on, Chris.
So, for calculus and curve sketching, we need to solve this in 7 easy steps, the first 4 of which can be easily found through just looking at and rearranging the initial equation which we have here. So the first 4 are finding the x-intercept and domain, the y-intercept and range, the limits approaching and at infinity, and the asymptotes. So our x-intercept and domain, we do not have an x-intercept for this graph, but the domain is x of the real number system, but x cannot equal -1, as that is where the asymptote is. So the y-intercept is 0, 2, and the range is y is anything of the real number system. Our limits approaching infinity, which we have right here, as x approaches infinity, it approaches positive infinity, and as x approaches negative infinity as well, approaches negative y infinity as well. So this means basically as the x value gets larger, it's reaching upwards, and as it gets lower and towards more negative numbers, it reaches the negative scale on the y-axis as well. So all that preemptive amble is over with now, and all we have to do is find the min and max. So what that is by using the first derivative of it to figure out what the critical values are, which is important in finding the points where on the original graph the max and mins occur. So our first derivative here we have written out. Here's the product and quotient law we have written here. And through that, we have our sign analysis, which we talked about earlier. So what we have is our positive, negative, negative, positive. Each value in itself is a 0 of the first derivative or where it does not exist. The zeros of this first derivative are negative 1.577 and negative 0.422. Negative 1 is also in this, as it's where the graph does not exist due to the asymptote. Another part of asymptotes, which we forgot to touch on earlier, is slant asymptotes, which is another way that the graph can not equal anything at all. So that's just a simple fix right here and really comes into play when we draw our graph. So for our max and mins, once again, we have our 2 points that actually occur when there's a shift. So when we were testing these points, as we talked about in the sign analysis, we noticed that the values of our test values went from negative infinity to negative 1.577, and from negative 1.577 to negative 1, the graph turns negative, and it reciprocates here as well on the other side of negative 1, and it turns positive on the other side of negative 0.422. Now what we have here is essential in learning curve sketching, as you need to state where your maxes and mins are. As we go from positive and negative, it's a maximum, as the derivative goes from greater than 0 to less than 0, showing kind of a bump-like formation. And our minimum going from here as it goes from the lowest possible to the highest possible. These are local maximums, minimums, as you can see them on the graph, because due to its tendency to go towards infinity, it doesn't necessarily end, but this is what's easier to make it a graph. Now we have concavity.
And basically with concavity, we need to find the second derivative of our original function. The second derivative of our original function. So as you can see, we've got the first derivative. We need to take the derivative again. So basically to do that, we use quotient rule yet again, and we end up getting 2 over x plus 1 to the power of 3. In our case, there are no zeros on the top as there are no variables. So all we have to deal with is the points that do not exist, which is at -1, just like before. So again, we put it on the number line. We have negative infinity here, -1 here, and infinity right here. As we have -1 as a point of inflection because f double prime goes from less than 0 to greater than 0, as seen on the board right here. So from negative infinity to -1, it is negative, meaning that it is concave down, and from -1 to positive infinity, it is concave up. And essentially, now that we have all of that information, we can go over to our trusty table over here. We need to line up the first derivative, the second derivative, and the shape that we are going to be dealing with, along with all of the different critical values that we have found throughout this entire process. So we have negative infinity, -1.577, -1, -0.422, and infinity. We label every single thing that we have found on our first number line. So we have positive to negative to negative to positive, and we have increasing to decreasing to decreasing to increasing, because that's what the first derivative allows us to know. With the second derivative, we have what we had right here, which means from negative infinity to -1, it is completely negative, meaning that it's concave down, and from -1 to infinity, right here, it is concave up, because it is positive. From that, we are able to derive the shape of the graph at these specific intervals. So as you can see, this line represents something that is increasing and is concave down. This one represents something that is decreasing and concave down. This represents something that is decreasing and concave up. And this represents something that is increasing and concave up. So finally, now that we have all that information, we are able to make our graph. As you can see in this graph, we have our vertical asymptote of -1 right there. We have our slant asymptote of 3x plus 1 right there. We have our y-intercept right there at 0, 2. And of course, we have every single line that makes up the graph.
Alrighty, and that's how you curve sketch. I guess I lost.
Oh shoot, he's filming. Oh crap. Alright. Where were we at?
Really, optimization, I think.
Oh, optimization. Okay. So next on our list is obviously optimization. And as you can see here, we have an example ready for you, but first, we gotta explain what it is. Optimization is essentially taking the different dimensions, lengths, heights, anything like that, and being able to maximize or minimize a different characteristic of it. For example, this is what we have. A poster has a total area of 125 square inches. The printed material has a margin of 3 inches on top and 2 inches on the side and bottom. Find the dimensions to maximize the area. So in this case, we have different dimensions of length and width. And as well as that, we're trying to maximize the area of what we have. So the information that we have allows us to make two different equations. Firstly, we know that length times width is equal to the total area. And we know that the total area is equal to 125. So simply put, our first one is length times width is equal to 125. And as well as that, we also know, due to this trusty little diagram that I have right here, that we have a margin of 2 here, 2 here, 2 here, and 3 here. So with that information, we're able to tell that the length is equal to length minus 4 for the two margins right here, and the width minus 5, and if you multiply those two, that should get you a maximum area. So from there, we have our second equation. Length minus 4 times width minus 5 is equal to the maximum area. After that, what we need to do is we need to rearrange one of our formulas, typically the one that we have the information for that does not have the maximum or minimum in it. So from there, all we need to do is divide the W over to make it 125 over W is equal to L. From there, all we have to do is simply put it into our other equation, substituting out the L with 125 over W, leaving us with 125 over w minus 4 multiplied by w minus 5.
This allows the formula to be solved.
Of course. Anyway, from there, all I did was expand it, leaving us with this. And after, once we finally have it as simplified as possible, we can take the derivative of this function. As you can see, we have 625 over w minus 4w plus 145. Taking the derivative of that leaves us with 625 over w squared minus 4 is equal to 0. And from there, all we have is a simple equation where we can rearrange to find the variable. From there, we push the 4 over to the other side, and we multiply the w squared over, and we divide the 4 back over to 625 side. So that leaves us with w squared is equal to 625 over 4, and so we square root both sides so that we can get w on its own, leaving us with a width of 12.5 inches. Once we finally have that information, we can substitute it back into our original equation to find the length. So if we put the w that we found here into this equation, 125 over... Well, you guys might have thought I forgot something on this board, didn't you? Ha! You guys have some good eyes. I missed the sign analysis, didn't I? But you already knew that. Let's get into it. As you can see, with this, all we have to do is plug in numbers into our f prime. So as you can see, if you put a number below 12.5 in, you get a positive number out of that. And if you put something bigger than 12.5 into the derivative, you get a negative number. As it's going from positive to negative, we know that 12.5 is a maximum, proving that what we did was correct. So next on the list, we have related rates. And essentially with related rates, what we're doing is basically we're given specific characteristics about a situation, and using rates and the other characteristics that we're given, we need to find an unknown, using implicit differentiation.
So with related rates, we have a problem here which is generally given in the form of a word problem. So our problem is the classical ladder sliding down a wall. So the ladder is sliding horizontally at a rate of 1 foot per second, which we have as d of x over d of t. The ladder, the hypotenuse, is 10 feet long, and the x-axis is 6 feet, and it's 8 feet off the ground. We found this using Pythagorean theorem to get the height of the ladder. So from here, we have our Pythagorean theorem listed up here, and we use the derivative of that to find related rates. So we have the derivative, and by adding with implicit differentiation, you have to add the respective derivative notation of it. So from here, then we simply fill in the variables with all of the information we found earlier. The hypotenuse is 10, replacing the c and the 2. The ladder does not change size, which means it's a 0 for its rate of change. The x-axis, multiply of 2 from the derivative. Length is 6, and it's moving at 1 foot per second, which gives us 12, which we see down here. So for the solution of the vertical axis, we have 2 times 8, as we see from our equation here. And because we do not have this variable, because we're looking for it, we do not fill it in with anything. So down here, we continue our equation, so 0 minus 12 equals 16 d at y over d at t. And then underneath, we further solve it. 12 equals 16 dy over d at t, negative 12 respectively. And from there we just divide the 16 across to solve for the one variable we do not have, the one rate. So now we have negative 12 over 16 feet per second equals d over y over d over t, and simplified to negative 3 over 4 feet per second. So here we're going to explain to you what an antiderivative is. An antiderivative is the exact opposite of finding a derivative of a function. It can be used to find integrals, area under a curve, as well as finding the original function when all you have is the derivative. Now, the equation for finding an antiderivative is x to the n plus 1 over n plus 1. So what we have for our equation here for our original f at x is 3x to the 5. So for finding the antiderivative, 5 being the n plus 1, 5 plus 1 is 6, and you put that in the exponent and the denominator as well. So you have 3x to the 6 over 6, which simplifies down to x to the 6 over 2. So that's for undefined antiderivatives, which are equal to whatever value of x that is unbounded can be inserted, and it has no range or domain like that. So we also have defined derivatives, which come into play in integrals, which we'll talk about in a little bit. And that is where you have a certain boundary for what the x values can be. We see that with the integral symbol here and the b and a value, which simplify the maximum, most positive x value can be, and most negative and lowest x value can be. So we have the integral bounded by 10 to 0. We have x squared minus 8x plus 9 d at x. So to find the antiderivative, we just simply, for every single value inside the equation, we perform the same operative as with the undefined. So we have x to the 3 over 3 minus 4x squared plus 9x, bounded by 10 to 0. So then, what we have to do is the first derivative test. And so that is where you input the equation of the top and most positive minus the most negative and bottom value. So for here, we wrote this out as, this is what is essential in getting questions right. You need f at 10 minus f at 0 is 70 over 3. How we got 70 over 3 is by plugging in 10 to all the x values. So 10 to the 3 over 3, minus 4, 10 to the 2, plus 9 times 10. And once we got all that, we did the same with 0. Now 0 is a special case in this scenario because everywhere you put in 0 in this will result in another 0. So it's the result of 10 minus 0, which is 70 over 3. You want to write it out on the final step here as the answer is equal to the integral of all of the initial formula you are using.
And what's essential to know is this is actually called the fundamental theorem of calculus. And that is a very important part of solving antiderivatives.
Thank you for listening to our TED Talk. Hey guys, so another part of finding the antiderivatives of simple and trig functions is that sometimes it's not that simple. Sometimes it's not the same as just a quick, easy, and opposite power law. So for here, we're going to teach you guys how to do u substitution. So what you're going to want to do is we'll have our original function here with the integral symbol, so meaning we need to find the antiderivative of it. So basically you're going to pick one part, generally the angle of each equation, and replace it with the variable u. So before you replace it with the variable u, you have a couple steps beforehand. So you'll choose which one you're going to change, and you'll also take the derivative of it. So du over dt, which is the derivative of u in respect to the variable t, which is what we're using instead of x in this formula. So the derivative of that is 2. So one of the other cool things about this is you have to rearrange the formula in order to solve for the variable that you first have in this equation. So you'll be rearranging for dt, which is du over 2. So once we get that down pat, we can finally substitute for everything. So we can sub in the u for the 2t plus 2, and we can also put the du over 2 and replace it for the dt. So once we do that, we can start to take the antiderivative of it. So we can get rid of the integral. Here's just some simplifying. And once we get down to it, we always have to, we get our answer here, which is at the bottom. But one of the things you always want to remember is once you take the antiderivative of it, is you want to not forget about that constant. Because with the constant, you always have it, but you never can tell what it is when you take the antiderivative of something. So you have to have it always add on, and that's as easy as putting plus c.
So simply all we got to do is take out these fractions, multiply it, get 10 over 6 on the outside, and finally, once we're at this last few steps, we can replace that u with what we originally put as 2t plus 2. So we put that back into the formula, giving us our final answer of 10 over 6 is multiplied by the square root of 2t plus 2 to the power of 3, plus that c, plus that constant. Now, of course, we also have to do that with trig functions, and u substitution works splendidly with that. So right now we have a function that is bounded by 0 to pi over 4, and it is sine x over cos cubed x. So what we're going to do first is identify what we're going to substitute with u. So in this case, we're going to do cos x. So from there, all we have to do is find the derivative of cos, which is negative sine x, and that's our du over dx, and rearrange that for dx, which would give us du over negative sine x. So once we have that ready, we can put that back into our equation for dx, leaving us with sine x over u cubed multiplied by du over sine x. And that's as easy as scratching off those sine x's right there, leaving us with du over u to the power of 3, which we can just flip onto the top as u to the negative 3 multiplied by du. After that, we can just take the derivative, or the antiderivative, should I say, of what we have using a basic power law, and we end up getting negative u to the power of negative 2 over negative 2. The negatives cancel out, leaving us with just u to the negative 2 over 2. Once we've finally gotten to this step, we can substitute our cos to the negative 2x back in, and we finally get our answer of cos to the power of negative 2x over 2. And after that, we just have to go straight over to the fundamental theorem of calculus, f pi over 4 minus f0, which is just what we're substituting into our antiderivative, giving us an answer of 0.5.
Thank you.
Is this on?
So another factor to antiderivatives and integrals that we need to talk about is some properties that take place that help you solve the solution properly and effectively. So with our integral equation, just our skeleton, we don't have any numbers, 'cause it's more of a concept than an actual idea. We have our coefficient in front of the initial function in itself. So one of the properties that you're able to do is bring out that coefficient from in front of the function. So that allows you to have the coefficient outside where it may not cause as many problems as it would have inside the function. Lets you solve the equation and make it easier when you arrive at your antiderivative, where you just simply multiply the coefficient through. Another factor to it is if you have two functions being added to each other inside the integral, if it makes it easier, you're able to split that up into two separate integrals that add to each other. Solving each one as a different antiderivative, maybe helping with some implicit differentiation, that sort of thing. And so that's for undefined or unbounded integrals. And this down here is just the same replica, just to show you that you're able to do it with bounded integrals as well. And this little portion over here is continuing also off of our last lesson, which shows you what happens if you accidentally switch the bounds on like the a and b values on the mean value theorem and the integral itself, because usually you're supposed to have your most positive and highest number that's farthest to the right on the top, and your most negative and lowest number on the left. That should be on the bottom. So this is the correct solution right here. It would be pi over 4 minus 4 when we put it into the formula here. But once we flip it around, you can see it gives us a completely different opposite number rather than this here. Well, what we're supposed to have, the equaling 1, get negative 1. We're supposed to have the 0.5, we get the negative 0.5 instead. Go. Hello, and welcome to Tyler's Private Corner. Today we'll be discussing the difference between the definite integral and the area under a curve. Now, as we'll learn later on in the video, area under a curve is exactly what it sounds like, area under a function's curve. And the definite integral is the total massive area within a certain function. Now, the difference between the two, because it can get confusing, especially for small-minded people, but it can get confusing and really hurt others. But honestly, the only difference, well, not the only difference, but the biggest difference, the most important one to know, that the definite integral is just your total amount of area. It can be positive or negative. It's just the total amount that's withheld by this function. And the area under curve it can only be positive. That's the difference between the two, because area can only be positive, just like everything else. All right, so now we're going to calculate the mean value of an integral of a function over an integral. So what we have here is our formula for the average of the function. And what that means is the mean value of a function is the average slope of the tangent line branching off of it. So we have our formula 1 over b minus a to the integral b over a f at x times d at x. And that also equals f at c, but we'll get into that in a little bit. Right now, we're trying to determine the average value of f at x when it's x squared minus 7x plus 10 on the domain 0 to 5. So we have our f average, and we just plug everything into the formula here. We put our equation in, put our domain in to the proper a and b values. So then we can, after we do that, we can take the antiderivative of it. So using the rules we talked about earlier, we get x to the 3 over 3 minus 7x squared over 2 plus 10x. And that's within the domain of 5 to 0. And we have the formula testing of the antiderivative of f when the function is 5 minus the antiderivative of the function while it is at 0. So now we've plugged in the 1 over 5 to it, so that's a little bit cleaner and easier to work with. We have x to the 3 over 15 minus 7x squared over 10 plus 2x to the domain 5 to 0, f at 5 minus f at 0. And so we have our average as well. We're just kind of simplifying it now. We're plugging in the 5 as we have in the past simulations. We're just kind of enacting this formula here. Plugging into the 5 to the equation minus 0, which we talked about as well earlier. So now our average is 125 over 15 minus 175 over 10 plus 10, giving us an average of 5 over 6. This is basically, we're going to get into f at c, and that'll be in our next lesson in a quick minute here.
And finally, with our final concept of the day, we're going to talk about area bounded between curves. So as you can see here, we have two different functions, 2x minus x squared as well as x minus 12. As you can see here, we're trying to find out what this area bounded between the two curves is. So to do that, all we have to do is first of all find out where their intersection points are. So as you can see right here, we will just set them both equal to each other. 2x minus x squared equals x minus 12, and solve as shown to get x equals 4 and x equals negative 3. Now we know that the points that they intersect are x is 4 or negative 3 on this side, and x is equal to 4 on that side. From there, all we have to do is do some integral work. So all we have to do is set the top function and subtract it by the bottom function. So 2x minus x squared minus x plus 12, as seen right here. From there, we have to simplify it down to negative x squared plus x plus 12, and we have to bound it by our intercepts. So as you can see here, we have negative 3 here and 4 right there. From there, we can do what we've been doing this entire time, find the integral or the antiderivative of this function that we have right here, and then, of course, put it into the fundamental theorem of calculus. Once you do that, you go f at 4, which is, of course, the antiderivative, minus f at negative 3 in the antiderivative, and finally, you get your answer, which is the area between the two curves, which is 343 over 6.